Hi students, in this video lecture we will continue our study of transform analysis, and we will be in particular studying about minimum phase systems. Okay, let's start. So let's start with the definition, what we mean by minimum phase systems here. Okay, this we already started discussing earlier itself in our earlier classes. When do you call a system minimum phase? If both the given system and its inverse, right? If both the given system and its inverse, if both of them are stable and causal, both of them are stable and causal, okay, then that system is referred to as minimum phase system. Then that system is referred to as minimum phase system. Okay, we already discussed it while in the pole zero plots also. So for this to happen, what should, in terms of poles and zeros, what could we say? All poles and zeros of that such system, particularly when it's a rational function, will be inside the unit circle. So once you could say all poles and zeros are inside the unit circle. That's what we could say about a minimum phase system, right? Why do we study them? Because they will be quite it would be quite useful to impose such additional restrictions. It's very useful to in lots of problems. Okay, so it's useful to impose such restrictions, okay, such constraints, such additional constraints, I would say, because anyway usually system being stable and causal is one constraint, but there's an additional constraint that its inverse is also causal and stable. So such additional constraints in certain classes of problems, in certain classes of problems. What are those classes? At least in this lecture we will take a look at two things. Okay, one of, okay, we will see that very shortly. After we go through the theory of it a bit, then we will come to that. Okay, another important point about minimum phase systems is it results in minimum phase delay. It results in minimum phase delay. Okay, minimum phase delay among all systems that have the same magnitude response. Among all systems that have the same magnitude response. To understand it better, we have already discussed in the earlier classes that multiple systems can have the same magnitude response, right? Despite having poles and conjugate, reciprocal conjugate poles and all, we have discussed in the last couple of classes. And the important thing that would happen in case of a minimum phase system, the systems for which both poles and zeros are inside the unit circle, is that they will have a minimum phase delay. Okay, that's why in fact to be more precise we should call them as minimum phase delay systems, but it's common to call them as minimum phase systems. Anyway, we will not go into the exact details of why they result in minimum phase delay, just we see it at this point of time as a property of them. Okay, now what we will do now is rational systems versus minimum phase systems. We will look into some of those properties now. Rational systems versus minimum phase systems. Okay, Well, let's start with we have seen that the statement that we are going to make now is mm, any rational. The statement that we are going to make now is that any rational system function, can be expressed as h of z equal to a minimum phase system h min of z and the multiplication of it with an all pass system that we discussed in the previous lecture. So a minimum phase system and multiplication of a minimum phase system and all pass system. So this is a very, very important theorem or property, whatever you call it. That means a given system response can be represented as concatenation of two systems, one having a minimum phase system and all pass system. Okay, this again, these are equivalent, not in terms of, yeah. So this is what the statement that we currently make here. Okay, if you want me to write it as a block in a block diagram manner, the way we could write it is, assume that you have a system whose z transform is h of z. Okay, the same thing, the equivalent representation of that could be, always you should be able to represent it as concatenation of two systems, one having transfer function of h min of z, one having a transfer function of h min of z, that concatenated with an all pass system, that concatenated with these two are equivalent system. That's what this statement does. Okay, let's now look at an intuitive proof for this thing. Let's try to prove this without loss of generality here. Let's consider that you could represent a given h of z as h min of z into let's say g minus 1 g inverse minus c conjugate, where for example the poles and zeros that are inside the unit circle, that you club them together, that would give you a minimum phase system. Okay, and then you club together the remaining, you keep it there. For example, here we are assuming just there is 1 0 outside, which otherwise h of z would have been a minimum phase system. So this is 0 outside the unit circle, 0 outside the unit circle. Okay, so what can we do now? So this means we have already discussed in the minimum all pass factors and other things that let's keep h min of z same. Okay, g inverse minus c conjugate, let's multiply it with a function that has another 0 which is inside the unit circle. This is outside the unit circle, so another inside the unit circle but having the same magnitude response. We already discussed it in the previous lecture. That would be equivalent to 1 minus c into z minus 1, would have the same magnitude response as here, but it will have a mirror 0 inside. So let's multiply and divide it so that it results in the same value here. Okay, Now what we do is here is we club these two here. Let's club these two terms together, right? So h min of z into h min of z into h min of z into 1 minus c times z inverse, and what is remaining here is equivalent to the remaining terms are z inverse minus c conjugate over 1 minus c into z minus 1. Okay, this just for the notational convenience, let me make slight changes here. Let me call this as h1 of z here. Let me call this as h1 of z, okay, which is this also let me call this as h1 of z, which is a min phase system to start with. Okay, so this I would call it as h1 of z. Okay, here also let me call this as h1 of z, so that later I would like to use that h min of z notation here, right, into 1 minus cz minus 1. Okay, so this is again, this is since c is outside, okay, the other one has a pole, a 0 inside. Now it's being reciprocal conjugate. So this let me represent with h min of z, right? And what about this? We have seen it, 1 minus c into z minus 1. This is nothing but an all pass filter. So this is equivalent to ap of z. Okay, therefore we are able to write h of z as h min of z into h all pass filter of z. Okay, although we considered here 1 0 is outside, you could also infer from here, it's extend here the same logic that even if you had a pole at outside the unit circle, you could apply the same logic, or you may be having both zeros and poles, but each one will have one all pass factor there, resulting in a generalized all pass filter there. Okay, this is the proof of it. So what is it that we are able to achieve now? Any given system can be represented as system function can be represented as a multiplication of a minimum phase system with an all pass factor. So that's what we are able to do so far. Okay, now let's see another relevant stuff here. So for that, let me switch to some slides here. Right, so let me show you a rational versus systems versus minimum phase systems with the help of this animation. The slides would be easier to understand. Assume that this is what you had as the initial h of z. You could notice here it has two complex conjugate zeros outside h of z. So what is it that we have done there to write it as a multiplication of a minimum phase system and an all pass system? We take a conjugate reciprocal of them, and then those are the ones which would go inside the unit circle, and you ignore for the time being those zeros outside. So then that system is essentially a minimum phase system. Everything is inside the unit circle. So the remaining terms you write it here, so which means the outside zeros we have not considered, they are there, and then these zeros have come which were not there in original h of z. So when we are trying to represent it as a multiplication of h of z as multiplication of h min of z and h ap of z, so we should have poles at that point, so that both the poles and the additional zeros that we have considered would cancel out. That's the basic idea for converting any rational system into a multiplication of a minimum phase system or an all pass system, right? So then why is it useful? So far we have seen in theory what it is. Assume that you are sending your discrete time signal over a communication channel to reach to the other end, and assume that there is some distortion happening within that system. So how do you get back your signal is the question. So you have initially the signal is S of n, you have sent it through a communication channel. What you got out of the system is SD of n, the distorted output. Okay, so how do you get back to your original thing? Obviously you have to put a compensating system, okay, which ideally should give you back S of n. So that's the basic idea. Okay, so assume that now you start assume that your distortion system is a stable and causal system, and what is desirable while you are designing a compensating system there? Obviously you want a stable and causal system again while you are creating that, right? So how will HD of z being stable and causal ensure or guarantee us to have HC of z to be also stable and causal? Not necessary. So essentially in a simple way, HC of z is nothing but 1 by HD of z. We have discussed that during inverse systems, right? So what we are will be doing and notice that we don't have the distorting system in our control. All we do is we model it basically. So its inverse being not HD of z, not necessarily might be having all its poles and zeros inside the unit circle. All we are assuming is that communication channel that which is introducing some noise is causal and stable. So what is usual practice followed is you decompose the HD of z into HD, a minimum phase system, and an all pass system, right? And after that your S of n, you are getting SD of n here, and that you pass through a compensating system whose transfer function is 1 over minimum phase system. Notice earlier it was 1 over HD of z, but rather in which need not necessarily be causal and stable, which is the desired property while you are designing a filter. Now the moment you decompose it into HD min of z and HAP of z, and then compensating system is having a transfer function of 1 over HD min of z, that is ensuring that your compensating system is also causal and stable. Of course it comes at a cost, the cost being your magnitude wise you are compensating it, but it would introduce some phase distortion, okay, which is inevitable anyway. So yeah, this is one of the very important application where you could get the same magnitude response despite provided you are able to, of course, model that using HD of you are able to model the distorting system with HD of z. You find out the minimum phase and then you take the inverse of it to get back. Okay, so that's your HD of z and HC of z. Your let z of z, the entire system transfer function is now HD of z into HC of z, right? And HD of z you have written as minimum phase system and all pass system, and HC of z is 1 over HD min of z. So you have an all pass equivalent to an all pass fact. All that remains is that all pass system. We have already seen in the previous class that this would give you the same magnitude like the gain magnitude gain of frequencies. Only it does is some distortion in terms of the frequencies. That's all that it would introduce. Okay, hope these slides are helpful for you to understand it clearly. Okay, now we have seen in terms of the theory of it and the proof how we could write, and here we have seen visually also how you could do that. So let's work out some examples on it right now. Okay, I'll solve a couple of examples, right, and then I'll give you 2 more examples for you to work out after watching this video. Okay, so first example, a simple example, is to understand how you be how you can decompose a given system into a minimum phase and all pass system. So let's take h of z equal to 1 minus 2 times z inverse divided by 1 plus 1 by 3 z inverse. The question is that express h of z as a concatenation of min phase and all pass systems, minimum phase and all pass systems. That's the question. Okay, right. How should we start here? Well, let's take first let's see in terms of the pole zero plot, and then we will go ahead after that. Okay, so first let's plot the pole zero plot of it, let's plot the pole zero plot of h of z. This is the imaginary axis, the real axis. Okay, how many poles does it have? There is only one pole. Where is it? So so let's take z common again, z plus 1 by 3. There is a pole at z equal to minus 1 by 3, right? And what about the zeros of it? Well, it has z minus 2. It has a 0 at z equal to 2. All right. Is it a minimum phase system? No. Why is it so? It's because the 0 is outside. So what would we do now? What should we do now? This, you would like to write it as a combination of minimum phase system. Well, how does the minimum phase system would look like? We are not going to alter the pole that's already inside, right? For 2, what do you take? You take conjugate reciprocal of it. Conjugate anyway, it's real, so that's 2 reciprocal 1 by 2. So that's 0.5, so half if that's the unit circle. Here you take a 0 there, the conjugate reciprocal, right? This is as far as h min of z is concerned. So this is real, imaginary. And how does now the h all pass filter transfer function would look like? Well, you introduced a 1 by 2 pole, which when multiplied with all pass should give you back h of z. There is no, sorry, 0 at 1 by 2, it's not there. So in fact, so to cancel that, you would be having here a pole at 1 by 2, right? In multiplication, the h min of z excluded a 0 at 2, that should be retained here at 2, right? Then this multiplication would give you this. That's all. This is what in terms of the pole zero plot. Okay, now let's take a look at in terms of mathematically, let's solve that out. So what is our h of z? H of z is given as 1 minus 2 times z minus 1 by 1 plus 1 by 3 z minus 1. What would we do now? So you better always remember this out while you are writing it as an all pass filter. What do you have? Our equivalent one, 1 minus a into z minus 1, z minus 1 minus a conjugate. So these are the couples. If you have one inside, you take the other out. Okay, so let's see here. There is no problem with the pole. There is only problem with 1 minus 2 into z minus 1. It looks like 1 minus a into z minus 1. So you multiply with g minus 1 minus a conjugate, which is nothing but 2. Here 2 conjugate is 2 only. Okay, you multiply and divide it so that you have the same term. And in order to get the minimum phase system, you take this out and you club those two terms together, you have g minus 1 minus 2 divided by 1 plus 1 by 3 g minus 1, and the remaining terms here 1 minus 2 into g minus 1 by g inverse minus 2. Okay, just again look here, in terms of this it's just inverse of it, so one so you even this of course it will have same magnitude even if you invert it, because its magnitude is 1, right? So this is your h min of z, and this is your h ap of z. That's all. Okay, hope you are able to follow that, and let's work out another example here. Second example. Now let your h of z is equal to 1 plus 3 times z inverse multiplied with 1 minus 1 by 2 g inverse over z inverse into 1 plus 1 by 3 z inverse. Again, express your similar to the previous example, express h of z as h min of z into h ap of z. Okay, that's what we'll again, it's a good practice to first draw like we did here. You write it in terms of a minimum phase system, alpha system, in terms of poles and zeros, then you work out mathematically. That gives you a good intuition. Okay, let's work it out again here. Let me have some space here. For later, let me save some space for drawing all pass filter. Okay. That circle looks pretty bad. Somewhat better, right? Let's look at the terms here. So this anyway z inverse, there are the poles and zeros at z equal to 0 are getting cancelled out, and then there is, let's first look at poles. There is one pole at z equal to minus 1 by 3, right? So z equal to minus 1 by 3, and then let's come to the zeros. It has two zeros. One zero is at z equal to minus 3. So there is a 0 at z equal to minus 3, and there is another 0 at 1 by 2. Okay, this is the real part, imaginary part, and this is h of z, right? We are going to express it first, h min of z. It's too long. I want to keep space for the other one, so that's good enough. Okay, and then we are not going to touch 1 by 2 here because that's already inside. I don't no need to touch minus 1 by 3. Okay, minus 3. Well, there is something happening here. You take the conjugate, that's minus 3 in itself, and then inverse minus 1 by 3. So that pole, instead of that, when you take a 0, it's coming at, it is resulting, and when you are trying to write it for a minimum phase system, it is resulting a 0 at z equal to minus 1 by 3. You had a pole at z equal to minus 1 by 3, so both get cancelled out here. Okay, this will not be there anymore here. Okay, I don't want to put a cross mark there because that again means as if it's a pole. Okay, but all I would say is, yeah, there won't be anything here essentially. Okay, this is your h min of z. Okay, and then what about the all pass filter? The real part, imaginary part, all pass filter, right? So -3, you have not touched anything there, is not is here, so you will have, what happened, yeah, you will have it -3 here, right? You introduced a 0 at 1/3, that has to be cancelled out, so you will have here at 1/3 pole. That's all pass filter, right? Now let's try to get the mathematical expression for this. So what we had for, what is our h of z? It was 1 plus 3 times z inverse into 1 minus 1/2 z inverse over z minus 1 into 1 plus 1/3 into z minus 1. First we are going to write its minimum phase expression. So what would happen then? Where is the problem is with this term? So again, you look at this, you always keep this in mind. On one side, if you have 1 minus a into z minus 1, other one is g minus 1 minus a conjugate. Of course, the numerator and denominator can exchange themselves, right? You had here 1 plus 3 into z 1, this is of this form, so that would result in g minus 1. This is not minus plus, so you have plus here, plus a conjugate, that's being real, z inverse minus 3. Okay, anyway, I would just remove this here in the interest of writing the whole expression in the same line, right? Into, you keep 1 minus 1/2 z minus 1, there is no problem with that. Okay, and I'll talk about z inverse, we will come back to it a little later, but let me for the time being put it in the all pass filter stuff. Okay, so here z inverse plus 3 I had kept there, so in order to cancel that I should have z inverse plus 3. I haven't included z inverse in the minimum phase, so let me keep it here in the all pass. Okay, and what else is remaining here? Anyway, 1 plus 3 z minus 1 is there, right? Now, yeah, if you hadn't looked at the pole zero plots, you might have felt there that it would have 2 poles and 1 0, but since we have seen it, it's now very clear that this in fact cancel this with simple multiplication factor. You take 3 out of it, right? That would give you 1 plus 1/3. So what is it that we got here? H of z equals to 3 into 1 minus 1/2 g inverse, right, multiplied with 1 plus 3 times z minus 1 by z minus 1 into z minus 1 plus 3. This representing as our h min of z, and this is your HAP of z. Okay, you might have thought why I kept 3 here. Well, unless otherwise specified, we usually try to have the magnitude of all pass factor to be 1. Okay, so we put that 3 here. Okay, the next question that you might get here is why the z inverse has been 1 by z inverse has been moved to all pass factor. What would happen had it been there in the h min of z? For example, how about, the question is this, how about h min of z equal to, for example, z minus 1, you keep it here, so that means 3z into 1 minus 1/2 into z minus 1. Okay, any idea about what would be the problem with this? Is there any problem? Yes, indeed. So you take the first term here, 3 into z power 1. So this is, the system is h min of z. Okay, there is no more causal. Okay, in other words, it is no more, it's not at all It's not a minimum phase system at all. It's important, minimum phase system at all. And so that's why we in fact moved it to all pass factor. And again, in all pass systems we already discussed that even with z power minus 1, if you multiply it and can take either positive or negative integer values, it would be still an all pass factor because its magnitude is essentially 1. So these factors it's important that should come only in HEAP of z, and this is the question that and not otherwise. Okay, with that, now what I will do is I will give you a couple of exercises for you to work out. Please make sure you work them out so that the concepts would become clear to you. Okay, the first exercise I would give you is another h of z function I will give you. So let your h of z for this exercise is, I will give you complex conjugate expression that has complex conjugate zeros. Okay, 1 minus 0.9 into e power j 0.6 pi, that's the angle, into z minus 1. Why complex conjugate pairs are there? That's a repeated question arising in different lectures. So it's essentially because that has to be h of n is real. That's as simple as that. Minus j into 0.6 pi into z minus 1, right? Multiplied with 1 minus 1.25 into e power j 0.8 pi z inverse. You have to have one more term here, multiplication. What is that? 1 minus 1.25 into e power minus j 0.8 pi into z inverse. So this is the function given to you now. Now express the same thing. You have to express h of z as h min of z into h all pass factor of z. Okay, then again you draw the way we were doing it. Don't just do mathematically, but also you draw the pole zero plots for all the three pole zero plots of h of z, h min of z, and h ap of z. That's the first exercise question for you. Okay, one more interesting question. Is let h1 of z is equal to z minus 4 multiplied with z plus 5 divided by z plus 0.5 into z minus 0.3. Well, let's say and then its ROC is absolute value of z greater than 0.5. You can see the original system is causal and stable, right? But it has zeros at z equal to 4 and minus 5, making it its inverse is non-causal, so it's not a minimum phase system. Now what we want is we want you to compute, okay, a causal and stable h2 of z that has the same magnitude, it has the same magnitude response as the inverse of h1 of z. So this is exactly the same question of what we had seen, a communication channel that is introducing distortion. Then what you do, you do it into h min of z and HAP of z, and h2 of z is essentially equivalent to 1 by h min of z. That's all. That's all what you have to compute here. Again, here also you draw pole zero plots as well. Pole zero plots of h1 of z. Okay, and then well, you could take that h min of z, pole zero plots. Okay, and then what else is there? H alphas of z, h2 of z. Okay, you plot all of them. Okay, that's all. We are done with the minimum phase systems. Yeah, I'll see you in the next lecture with another topic in transform analysis. Okay, right. Have a great day. Thanks for watching. Bye. Take care.